On the first day of class, I mentioned to you that we will be doing 2 projects in this class. One project is the big project that you will do with your group. This project will last the whole semester. In general, before spring break, you will be doing the parts of the project that come before prototyping. After spring break, you will be doing the parts of the project that include prototyping and testing. Before spring break, we are also going to do an individual mini project related to motor modeling. The purpose of this project is to familiarize you with the level of engineering required for your project. In this assignment, you will learn about the modeling, experimentation, and design parameters you need in order to understand how to utilize a permanent magnet DC motor in your project. The purpose of this video is to get you started with your motor modeling project. So here's the setup for this mini project. Your company has decided to develop a self-balancing hoverboard for cats. The system consists of a DC motor attached to a belt drive, which then attaches to 2 wheels. On board is a motor controller, battery, housing, and Bluetooth communication for throttle and brake. The choice of motor, battery, and belt drive are up to you, the designer. Your company has created 4 target performance specifications as follows. The system must propel the hoverboard up a 10-degree smooth concrete ramp while loaded with a 3-kilogram rider at a speed of 3 meters per second for 1,000 meters. You need to choose 3 things: the motor, the battery, and the transmission and transmission ratio. We are going to do this over 6 weeks as follows. Week 1 includes the free body diagram, forces, torques, and power. Week 2 will be about mechanical loss, friction, and damping. Week 3 includes motor selection and design, including things like power, torque, and speed. In week 4, you will do transmission ratio selection. In week 5, you'll do battery selection, and in week 6, you will do some motor testing. Today starts week 1, the free body diagram. You have an assignment on this. To help you get started on your assignment, in this video, I'm going to remind you of some things about free body diagrams related to wheels and ramps. First, I am going to draw a wheel here. In a free body diagram, we want to draw in all of the forces on the wheel. One force that is good to start with is gravity. As a reminder, gravity always acts on the center of mass of the object. So if I assume that the wheel has a uniform density, then the center of mass will be right at the center. So I'm going to do that here. Right now, I'd like to point out that this wheel is not in equilibrium. When something is in equilibrium, that means that all of the forces cancel out. Also, the object won't accelerate at all because the sum of forces is 0, and we know that F equals ma, force equals mass times acceleration. Since force equals 0 when an object is in equilibrium, and the mass does not equal 0, that means that the acceleration will be 0 when the object is in equilibrium. Now, most of the time, gravity won't be the only force acting on the wheel, because the wheel is probably sitting on a surface, not just floating in space. Let's put the wheel sitting on a surface. Now, we not only have gravity, we also have contact forces. We know from Newton's laws about equal and opposite forces. The wheel will push down on the floor, and the floor will push back up on the wheel. If we know that the wheel isn't accelerating, like it isn't falling through the floor, then we know that the force of the wheel pushing down on the floor will be equal to the force of the floor pushing back up on the wheel. Now, in our mini project setup, we have a wheel that is not sitting on a flat surface, but is sitting on a ramp like this. Now, you know from your experience with the world that the wheel, just left alone, will roll down the ramp. But why does this happen? Let's draw the free body diagram. The wheel has gravity acting on it like this, and the ramp will push back on the wheel like this. Now, notice how this force isn't directly underneath the center of mass. It is off-center. To deal with this, we need to remember what we know about moments and torques. A moment is a force that causes something to rotate, and it is equal to the force crossed with the radius. Cross means we multiply only the parts that are perpendicular. To figure out how much force is perpendicular to the radius, we have to break down this force into components that are in the direction of the radius and perpendicular to the radius, like this. Finally, we know that just as F equals ma, moment m equals I times alpha, or we could also call this torque, T equals I times alpha. Alpha is the rotational acceleration of the wheel in radians per second squared. We can take this moment calculation and plug in some of our knowns. The moment of inertia of a solid disk is mr squared over 2. I just looked this up. And the moment is F times the sine of theta times the radius of the wheel. And we know that this force is mass times gravity, since it's equal and opposite to the force of gravity. So we can use all of these things to figure out alpha, the rotational acceleration of the wheel. And this will allow us to figure out how fast the wheel will roll down the ramp. Notice that we've left everything that we could as a variable, so that we could figure out how fast the wheel will roll down the ramp for different values of mass, wheel radius, and angle of the ramp. Now, in your project, you're not just interested in how fast this wheel will roll down the ramp. Instead, you're interested in how much torque is required to rotate this wheel to keep it from rolling down the ramp, and how much torque is required to get the wheel to roll up the ramp at the required velocity, and things like that. Now, let's take a look at your assignment for Thursday. Step 1 is to create a free body diagram for the wheel. Draw and label all important variables and design parameters in your diagrams and include dimensions, forces, velocities, angles, and vectors. Identify all forces acting upon each subsystem, including gravity, interaction forces between subsystems, and ground reaction forces. Here, subsystems refer to the different parts of this hoverboard. For example, the hoverboard includes a wheel, but it also includes a motor. The motor will exert a torque on the wheel, just like the ramp reaction forces exert a torque on the wheel. Question 2 says to solve for static equilibrium. In other words, can you figure out how much torque the motor would need to exert on the wheel in order to get the wheel to stay stationary, not accelerating up the ramp nor accelerating down the ramp? Using the information we went over today and using information that you know from having taken physics, see how many of the questions in the assignment you can get through before our next class, and come to class ready to ask questions. We'll have one day in class to ask questions before this assignment is due.